This video describes the Autopilot system I developed for the final project of my master's degree in computer engineering from San Jose State University. The Autopilot serves as the application, but the main goal of this project was to learn how to integrate a real-time operating system into a relatively complex design. This included learning how to write drivers to allow interaction with hardware. I also wanted to gain experience with the I2C serial bus and RTOS API functionality, as well as a variety of sensor hardware. As an added bonus, I got to learn something about Autopilot design. The system is built around an LPC 1769 microcontroller from NXP. This microcontroller uses the Cortex M3 processor core from ARM, and it is mounted on an LPC Expresso development board from Embedded Artists. The system runs the free RTOS real-time operating system. 5 sensors are used to determine aircraft location and altitude. The microcontroller communicates with 4 of the sensors using I2C. These are the 3-axis accelerometer, 3-axis magnetometer, 3-axis rate gyroscope, and the barometer. The GPS receiver uses a TTL-level UART interface. The accelerometer is the analog device's ADXL 345. The magnetometer is the Honeywell HMC 5883L. The gyroscope is the L3G 4200D from ST Microelectronics. Barometric pressure is sensed by the BMP 085 from Bosch. These sensors are all mounted on evaluation boards from SparkFun Electronics. The GPS receiver selected for this project is the GS407 U-Blox 5 unit with a helical antenna. The Autopilot sends servo commands to one of Pololu's MicroMaestro servo controllers over a TTL-level UART interface. These commands, along with the human pilot's commands from the ground transmitter, are fed into Pololu's servo multiplexer. The human pilot toggles a switch on the ground transmitter to tell the multiplexer to listen to either the human pilot or to the Autopilot. This allows the human pilot to resume manual control at any time, even if the Autopilot is malfunctioning. 5-volt power is regulated by a Castle Creations CCBEC, which steps down the flight battery's voltage. This directly powers the radio control receiver, the servos, and the 2 Pololu boards. It also feeds 3 SparkFun Li-Power 3.3-volt switch mode power supplies, which power the remaining hardware. Several components are mounted on the exterior of the fuselage. The reset and ISP switches are used to reset the microcontroller, as well as to force it to enter bootloader mode. The Zigbee transceiver is also mounted on the exterior of the fuselage. The 4 status LEDs indicate the current state of the Autopilot system. When the system is initializing its sensor hardware and calibrating the gyro 0 point, it cycles the first 3 LEDs. The first LED then illuminates to indicate that initialization has completed. The second LED indicates that the Autopilot has been enabled and is controlling the aircraft. The third LED indicates that the home location has been initialized. The fourth LED indicates GPS receiver status. Flashing indicates that messages are being received from the GPS receiver, but the receiver does not have a lock on location. Solid illumination indicates that the GPS receiver has obtained a location lock. If the fourth LED does not illuminate, it means that the Autopilot is not receiving information from the GPS receiver. This indicates an error condition. FreeRTOS allows the system to run multiple tasks at different priority levels using a preemptive scheduler. Most of the hardware drivers use an interrupt service routine and a helper task to communicate with the hardware. The interrupt service routine returns data to the helper task in a message queue, or it uses the semaphore to signal the helper task to wake up and perform an action. The Autopilot is programmed with waypoints that consist of latitude, longitude, and altitude. When enabled, the Autopilot flies the aircraft in a path to hit each of the waypoints in succession. When the waypoint course has been completed, the Autopilot flies to the home location and enters a holding pattern. It remains in the holding pattern indefinitely until the human pilot resumes manual control. Takeoff and landing must be done manually. If the Autopilot is engaged prior to the GPS receiver getting a lock on location, the Autopilot will attempt to level the wings and pitch the nose up approximately 5 degrees from horizontal. By manually pitching the aircraft up and down, it is possible to see how the Autopilot controls the elevator in an attempt to set the pitch angle to +5 degrees. Pitching the nose up high leads to down elevator control. Pitching the nose down low leads to up elevator. If the aircraft were flying, these elevator deflections would drive the aircraft to the target pitch angle. Similarly, rolling the aircraft back and forth causes the ailerons to deflect in an attempt to level the wings. The control gains were increased for this demonstration to make it easier to see the control surface deflection. Also be sure to check out the flight demonstration video to see this project in action.